What is up, my junior scientists? Hope you all are doing good and in the best of health. Today, let us take a look at a question from JEE Advanced 2016 rotation chapter. So he has given that there are two thin circular discs of mass m and 4m having radii a and 2a respectively. So these are two thin circular discs that you are seeing here, and they have a radii a and 2a, and the masses are m and 4m. I have shown you these discs as a ring with spokes because it will be very easy for you to visualize when this is rotating. Okay, so remember that these both are two discs. They are rigidly fixed by a massless rod of length L equals to root 24a through their centers. So he's saying that these both discs here are fixed by a rigid rod of length L. Also, he has given the relation between L and A, where L equals to root 24 into A. This assembly is laid on a firm and flat surface and set rolling without slipping on the surface, so that the angular speed about the axis of the rod is omega. So this whole assembly rotates about this axis, this rod, with angular speed omega. To help you visualize that this whole assembly is rotating about this point, okay, is rotating about this point, I have extended this rod from here to here. Okay, this rod is not given in the question, but I've just extended it from here to here so that it is easy for you to visualize that this whole assembly rotates about this point. Okay, so let us have a look at the schematic. Okay, so you can see that this whole assembly is rotating about this rod, which is connected between these two discs with an angular speed omega. And one more thing you can observe here is that there is no slipping in this case. These both discs are in pure rolling. Next, the angular momentum of the entire assembly about point O is L. So he has given us that this point is O. Okay, if you extend this rod where this extension meets with the ground, that point is O, and the angular momentum of this entire assembly about this O is capital L. This was a multiple correct answer question, so let us analyze each option and see whether it is right or wrong. So the first option which was given was the center of mass of the assembly rotates about the z-axis with angular speed omega by 5. So the first question, the center of mass of the assembly rotates about the z-axis with angular speed omega by 5. So this is our z-axis, right? And this is our center of mass. You can observe it is a little closer to this larger disk. So as this assembly is rotating, the center of mass also will rotate about the z-axis. Let us have a look at the path of the center of mass as this assembly rotates about the z-axis. So this blue dot that you see here is the center of mass, and this is a vector which is joining the z-axis to the center of mass. So you can see that the center of mass moves in a circular path, and we need to find what is the angular speed with which the center of mass moves in a circular path. Also, what we can say is the rate of change of angular displacement of this vector, this blue vector that you see, is the angular velocity of the center of mass. To simplify analyzing this question, we are going to consider the pure rotation of this body about two axes and combine these two rotations to get the net motion of the body. The first is pure rotation of this assembly about this axis. So here we can see that this is the axis and this two discs rotate about this axis. There is only pure rotation and the angular velocity vector points in this direction, which you can see here. The next axis that we are going to consider the pure rotation of this body is about the z axis, right? So the body here or the assembly is moving in pure rotation about the z axis. See, they are not rotating about this axis. There is only this axis, z axis, and this whole assembly is rotating about the z axis. We are going to combine the first case and the second case, which would result in the motion of the body as he has mentioned in the question. We can observe here that the center of mass of this assembly goes around the z axis with angular speed omega z. So basically what we need to find is, we need to find this omega z in terms of omega. The concept which we'll be using here is that in the combined rotation about the two axes which we are considering, he's saying that the points here, so he's saying that this assembly is in pure rolling, so the point which is in contact with the ground at a particular instant, this point velocity is 0, okay? This point velocity is 0 at that particular instant. So we will calculate the velocity of this point due to each of the two omegas, and we have to equate it to 0. Let us consider the first rotation, which is about this axis. This axis is the one which is joining both the discs, okay, and the angular velocity of this assembly about this axis is given as omega. So if we want to find the velocity of this point here on this wheel, okay, we are taking the point which is in contact with the ground. So the velocity of this point on the wheel or on the disc due to this omega will be omega into 2a, right? So the velocity of this point due to this angular velocity will be 2a into omega. Next, we will consider the rotation of this whole assembly about the z-axis. So the velocity, again, we will take the velocity of this point which is in contact with the ground. It is given in the question that this length is 2L. This is L and this is L. So this whole thing is 2 times L, and this is L 2L, and this length here is 2A. Okay. And one more thing that he had given is L equals to root 24A. So this whole length is 2 root 24A, and this is 2A. As this is a right angle triangle, we can calculate the distance from here to this point which is in contact as 10 into A. So the velocity of this point on this assembly about the z-axis, if we are considering only the rotation about z-axis, it will be 10a times omega z. So which I am writing here 10a times omega z, and I am representing it by this vector here. So let us have a look at the schematic in this case. So you can find the velocity of any point due to this omega z by just drawing a vector there and doing omega z into the radial distance of that point from this axis. We are interested in the bottommost point, so we have drawn a vector from this axis to the bottommost point and calculated the speed of this vector. You can see the velocity is pointed in this direction. It is represented by this arrow. Now let us combine the two rotation motions that we have discussed. So we are considering the velocity of a point which is in contact with the ground on this disk. So the velocity of this point due to this rotation is 2a into omega, and due to this rotation is 10a into omega z. As the body is in pure rolling, which we have written here, the net velocity of this point must be 0. So we can write 2a omega minus 10a omega z equals to 0. So we can say the angular velocity of this body about z axis is omega by 5. So this was the first question. So the first option which he has given is a correct option. The next option is the magnitude of angular momentum of the center of mass of the assembly about point O is 81 ma square into omega. The angular momentum of any body about a point is given as L bar equals to m into r bar cross v bar. Here m is nothing but the total mass of the assembly, which is 5m. R bar is the position vector of the center of mass with respect to point O. So if the center of mass is here, approximate location we are taking. So this R bar is nothing but this position vector from O to the center of mass. And V center of mass is the velocity of the center of mass. So this angular momentum can be calculated using this formula. One more thing I want you to note here is that R bar is in this direction and V bar is in this direction. So as angular momentum is perpendicular to both R bar and V bar, you can see this is the direction of angular momentum of the center of mass about point O. Before going into calculation of this value, let us visualize and see how this angular momentum vector changes with time. So you can see that the center of mass is moving in a circle. The R bar cross V bar is perpendicular to both R bar and V bar, and this vector is also changing with time. You can see the direction of this vector is changing with time. Its magnitude is constant as the length is constant, but its direction keeps on changing with time. So the angular momentum formula is m into r bar cross v bar. Let us first calculate what is r bar. So this disk here is at a distance L from O, and this disk, the bigger one, is at a distance 2L from O. So we'll just use the center of mass formula, m into L. So this m into L plus 4m into 2L. So this is 4m, and this whole thing is 2L divided by total mass. So if we calculate, we get R center of mass as 9L by 5, or the magnitude of this distance here from O to the center of mass is 9L by 5. Next, let us move on to the calculation of velocity of the center of mass. Now how we will calculate the velocity of center of mass is, we will first find out what is the instantaneous axis of rotation. Next, we can calculate the velocity by using the angular velocity about the instantaneous axis of rotation and the distance of the center of mass from that axis. So we had considered the angular velocity of this body about two axes. One is this axis and the other is the z axis, and we found out that the angular velocity about that axis was omega by 5. Now we know that at a particular instant, these 2 points which you see here, okay, they are at rest at that instant. So if we join these 2 points, okay, if we join these 2 points, we will get an axis, and we can say that this whole body at this instant is pure rolling about this axis. This axis is also called as instantaneous axis of rotation. It is not that this instantaneous axis is fixed in space. This instantaneous axis can move in space with time. So we can say at this instant, the resultant of these 2 omegas, this omega by 5 and this omega, is this vector. So the net angular velocity of this body at this instant is pointing in this direction. And as this omega by 5 does not have any component on this, the component of omega along this will be omega cos theta. We calculated that this length from here to center of mass was 9L by 5. So this distance here that you are seeing will be 9L by 5 sine theta, where this is the angle theta. So we can calculate the velocity of center of mass by omega times the distance from the center of mass to this axis. So V center of mass, the velocity of the center of mass, equals to omega cos theta. Omega cos theta is about this instantaneous axis of rotation times 9L by 5 sine theta. So the distance of this point from this axis is 9L by 5 sine theta. We are writing that here. Let us now put in all the values here so as to calculate the angular momentum. One more thing that you notice here is r bar and v bar are perpendicular. So we can write this as 5m into r center of mass into v center of mass. When we put in the values, we get L0 equals to 5m times r is 9L by 5 into v center of mass is omega cos theta into 9L by 5 sine theta. We can calculate the values of sine theta and cos theta from this triangle. It is given that this is root 24a. The radius of this disk is a, so this will be 5a, and we can calculate the sine theta cos theta values. So in this expression, if we put the value of L as root 24a, sine theta as a by 5a and cos theta as root 24a by 5a, we get the value of L0 as approximately 78 ma square omega. In the option he had given 81 ma square omega, so that is not a correct option. The next option is the magnitude of angular momentum of the assembly about its center of mass is 17 ma square omega by 2. So if we look at this assembly from the center of mass frame, it will be seen like this. So this is just 2 disks rotating about a given axis with angular speed omega. So the mass of this disk here is m and its radius is a. So its moment of inertia will be ma square by 2. So the moment of inertia is ma square by 2. It is rotating about this axis with omega. So the angular momentum is ma square by 2 into omega. Next, for this disk, this is mass 4m, radius 2a. So m 2a whole square divided by 2 into omega. So we get the angular momentum about the center of mass as 17 ma square omega by 2. So that is also the correct option. So the option 3 is the correct option. Let us now check the last option. Saying the magnitude of z component of L is 55 ma square omega, where L is the angular momentum of the entire assembly about point O. So we see that this is point O and this L is the angular momentum of the entire assembly about point O, and we need to find the z component of the angular momentum. So we know that the angular momentum of this entire assembly about O is angular momentum about its center of mass plus the angular momentum of the center of mass about O. So these are the two vectors, and the net angular momentum is sum of these two vectors. We have found out the values of these vectors in the previous question. Now the sum of these two vectors in the z direction will be LCOMO cos theta minus LCOM sin theta. So the z component of center of mass is LCOMO cos theta minus LCOM sin theta. One more thing, we are writing this as theta here, as we know the angle between this and horizontal is theta. So this will be 90 minus theta and this angle will be theta. We know that this angle here is 90, and if this is theta and this is 90, this will be 90 minus theta. So that is why I marked this as theta and 90 minus theta. So previously we had found out that LCOM about O, the angular momentum of the center of mass about O, was approximately 78 ma square omega into cos theta minus the angular momentum of the assembly about center of mass we found as 17 ma square omega by 2 into sin theta. If you put the value of cos theta as root 24 by 5 and sin theta as 1 by 5, we get Lz approximately equal to 75 ma square into omega. So this is not equal to this. So this is also the incorrect option. So the correct options in this question are, the first is the angular speed of center of mass, which is omega by 5, and the second is the total angular momentum of this assembly about center of mass, which is 17 by 2 ma square omega. So I will sign off here. If you like the video, if you have benefited from it, do like, share and subscribe. One of my students requested me to do a video on banking of roads. So the next upcoming video would be about banking of roads. So lots of good visuals and concepts coming up. So to stay updated, hit the subscribe button and you'll get regular updates.